Here is Mr. Vishnu Kesaraju, and he's from the biomedical, and that's things like that. So the bulk of the speakers have been this time, and his topic is an integrated approach to simulation, combining process and event-driven models.
Okay. Good morning, everybody. I'm Vishnu Sharma Kesaraju, and my topic is an integrated approach to simulation combining process and event-driven models. My advisor is Dr. Sharma. In this presentation, I'll be briefly going over the literature review I have done. And I'll be talking about the integrated entity event simulation framework. Then I'll move on to some of the important components of the simulation framework, that is resources and queues, then process components, and the most important part of my research, enhanced modeling using entities in integrated entity and event environments. Then I'll be talking about the development of the entire framework, and also the framework testing is one of the part of my research. As engineers, we all know that simulation is very important to analyze as well as to verify various strategies and this makes very important tool in our engineering projects and our decision making process. And also, along with the growing potential of computers, the significance of simulation as a decision making process is growing. So the importance of simulation is because due to the fact that it answers the what if questions. As defined by Shannon in 1998, he defines the simulation as a process of designing a model of a real-life system and conducting the experiments with that system and model, and understanding the behavior of the model system, and also evaluating various strategies for operation of the system. And we can find the applications of simulation in various fields like healthcare systems, military applications, and also computational biology. Today, as of now, simulation software evolved from more general purpose language like Pascal, Fortran to specific simulation packages. Simulation models can be classified based upon three dimensions like time, change of state of system like state variables, and also the involvement of the randomness. This is one of the popular classification given by Kelton et al. In 2004. He classifies the simulation models like in terms of time, like static models and dynamic models. In static models, the time would be constant, such as Monte Carlo simulation. Monte Carlo simulation is also can be classified as a stochastic simulation models, and also dynamic models in which the time evolves as the simulation progresses. And depending upon the change in the state of the system, simulation models can be classified as continuous and also as discrete. In continuous models, the state of the system changes continuously over the time, and they are usually represented by differential equations. On the other hand, discrete simulation models, the state of the system changes a discrete set of points as the simulation progresses. Another classification is depending upon the involvement of randomness. They are deterministic models and stochastic models. Deterministic models have predetermined inputs and they have corresponding specific outputs. Where, on the other hand, the stochastic models, one or more inputs can be represented as random variables, and the resulting outputs are also random. My research focuses is in the area of discrete event simulation. Discrete event simulation, as we discussed um, the classification, is considered as a discrete, dynamic, and stochastic. Discrete because the state of the system changes at a discrete set of points. Dynamic because as time progresses, simulation progresses, and stochastic because involvement of one or two random, more than one random variables as inputs. So, unlike analytic models, discrete simulations models are run rather than solved. And some of the typical steps in a simulation study are problem definition and formulation, in which the simulation modeler makes sure that there's a consensus on the problem they are solving, and they decide if the simulation is the right kind of tool to solve that kind of problem. Project goal and planning, and at this stage, um, simulation model comes up with the different alternatives and the methods of evaluating this simulation model and measures of effectiveness. And in the data collection stage, the simulation modeler has to determine, analyze the data for the proper distribution to give it as input to the simulation model. And model translation to be transferred, the simulation model is, the simulation model has to decide which kind of language, programming language or package it has to use for the simulation. And, and, and the model is transformed from a conceptual level to the physical simulation model. Verification validation, in that stage, the simulation model is debugged for any errors, and also the calibrated with the real life systems. These are the few important terminologies that I would be using frequently in the presentation. So I'll go through the important terminologies like entity, events, state variables, attributes, entity and event list, and resource and queue, and of course clock. Entities can be defined as object of interest that move around the simulation model, change the status of the system, and they get affected by other entities, and also they affect the other entities. Events are the instantaneous occurrence that changes the state of the system. State variables are the set of variables that describe the characteristics of the system, and at any given point of time. And attributes are the properties of the characteristics of the entities. Same as the state variables. State variables are the characteristics of the system, and attributes are the characteristics of the entity. And event lists are the list of events to occur in the simulated future. So, the general functionality of the event list is to sort the list of events that are to occur in the future, and the simulation engine picks up the most recent event, and it will be scheduling that event, or it will be processing that event or entity. Just as entity list. Entity list is also the list of the entities that are to be processed in the future, simulation future. Another important term is the delay. Delay is defined as the duration of time of undefined and indefinite length, and it is not known until it ends. And another important terms are resource and queues. Resource is a source of supply or support in the that means that which can be occupied by any entity, or else, for example, in manufacturing systems, the resource represents personnel, equipment, or any machine or a storage space. And queues are used in the simulation model for the entities to wait for the resources. And simulation clock is a variable that keeps track of the simulation time during the simulation run. So I'll take a simple example from the real world life and the real world, and try to explain the two different views: event-oriented models and process-oriented models. For example, consider this simple example. Consider a restaurant, and one person is working in that particular restaurant to serve the customers, and this one customer walks into that restaurant. He places an order, waits for the order to be processed, and after the person who's working there, employee, he serves the order, and this particular customer takes that order and gets out of the system. So how that example can be related to the event-oriented models and the process-oriented models. This is a server. That means he's working over there. And first, an arrival of the customer occurs. That means in the event-oriented world, we have arrival event occurring there. While on the process-oriented world, a create process creates an entity, and that particular entity seizes the resource. That means he places an order with that particular server, and server takes that order, works on that particular order. That means he goes through a delay process. So we have a seize process, delay process, and create process, seize process, and delay process. While the customer is being served, if another customer walks in the event-oriented model, we have another arrival occurring there, another arrival event occurring there. While on the process side, we have another create process going on that creates a customer or entity, and this second customer also tries to seize the process, seize the server. But the server is busy with the first customer or entity, so he has to go through a delay process. That means he waits in a queue. So we have two processes occurring here: create process and delay process. So as you can see in this chart, the in-service entity, the entity arrived at the time 0 is in service, and the entity that arrived at time 5 is in queue. The first customer's order has been served and he leaves the system. So on the event oriented side, we have a departure event, or else we can say finish event occurring. On the process oriented side, we have a release process going on. Release process releases the server, and again after release process he goes through a dispose process. That means the entity is disposed of the system. After the entity gets disposed of the system, cease process occurs. That means the first customer, the second customer who is waiting in the queue, immediately sees that particular server. So the customer waiting in the queue at time 5 moves from queue to in service. This also he's also leaves the system after some time. Okay, so we have two models here: event-driven models and process-driven models. So in event-driven simulation, events are the fundamental actions that change the state of the system, and the change of the state of the system occurs at events, and they are represented by nodes. So the Q and S are the Q's are the state variables that represent the state of the queues and resources, and the scheduling of future events is represented by the arcs between two nodes or two vertices. And whereas the process-driven models, it is a higher, represents higher level abstraction than the event-driven models. And as we discussed in the earlier example, an entity is created in the create process, it goes to the cease process, and then delayed and releases the server and get disposed of. And in my research, I'm integrating these two approaches: process-driven approach and event-driven approach. Why is it important to integrate these two approaches? Because both of these approaches have different advantages, and I want to combine these two advantages into one single simulation framework. The advantages of event-driven approach is that we have control, flexibility with regards to attributes of the entities, state variables, and the logic flow. And as stated by Bus et al. In 2001, event graphs or event-driven models are very powerful. They are such powerful that every model that can be represented in process worldview, can be represented as an event-driven model, but the reverse is not true. And the process-driven approach. The process-driven approach are very popular. They are popular because it's easy to model the real systems, and they follow the basic process-driven model. Any framework follows a commonly understood flowchart approach. And also we can have a direct mapping of the simulation logic to the model animation. Because of these features, overwhelming majority of the discrete event simulation tools today are discrete process-driven model. I'll briefly go to the simulation framework I have developed. The integrated simulation framework that I have developed has two main components: E-square. E-square stands for entity event. E-square integrator, E-square model. The main functions of the E-square integrator is to establish effective communication between entities and events. And another important function of the E-square integrator is to handle entities and events efficiently. And the E-square model provides hierarchical modeling capabilities with process-driven and event-driven components. As you can see here, we can see the E-square integrator here, and this is the E-square model. E-square integrator has access to entity list and event list. These entity lists and event lists maintains the prioritized entities and events respectively. And once the simulation starts running, the E-square model populates the entity list and event list with entities and events respectively, and they are accessed by E-square integrator. The E-square integrator takes out the entities and events, earliest entity and earliest event, and compares the simulation time between them two. And the earliest entity or event is sent to the processor, and it updates the simulation clock and sends it to the processor. The processor sends to the appropriate block or event node to get the simulation processed. And how are we integrating the process-driven, event-driven model in a process-driven model? Our process-driven models are based upon our simulation framework is based upon process-driven models, and we have a data structure that supports the blocks. What we are doing is we are including an event graph block, which is very similar to any other process block, and we are including in it. This event graph block acts as any other process block, but it also acts as a workspace for event-driven models. These are some of the implementation details of the simulation framework, integrated simulation framework. We have an important class called simulation, and it has a method called manage simulation. Manage simulation calls the model class. The model model class reads the model from the user, and it also creates blocks and nodes, event nodes. And when the simulation is running, it calls it takes out the entity or any event from the entity or event list, updates the simulation clock, and process the entity or process particular event. Another important feature of the simulation framework are the resources and queues. This particular feature, integrated simulation framework explicitly models the entity flow at the event level, and but the entities, but the process-driven models are event-driven, and event-driven models are two different things, and they have they interact with the resources or queue in a different manner. So, in order to integrate these two things with the resources and queues, what we have done is we have come up with the intermediate layer. In that particular intermediate layer, we have placed the resources and queues. The main objective of coming up with the intermediate layer is to have a controlled access over resources and queues, and also effective management. If you look at the model class, we can see the vector of resources and queues. We have placed that resources and queues in the model class to centralize the control. As already defined, resources are any machines, operators, or any finite capacity objects which the entity compete for. And queues, when our queues are defined as a place for entities to wait when the resource is busy or occupied. If you look at the resource class, we have methods to release the resources, assign a resource to a particular entity, and check if the resource is available, and so on. And in the queue class, we can check the queue if it is empty or not, and insert an entity into the queue, and remove a queue entity from the queue. Okay, I would be spending less time on this particular topic. See, resources can be in one of the three states. It can be idle, busy, or failure, breakdown. So when the resource is not processing an entity, it is said to be in idle state. If it's processing an entity, it's said to be in a busy state. But if the failures can happen, the failures are like random events. When it occurs, the resource state changes from idle or busy to breakdown state. So this particular framework also has carefully modeled the resource failures in it. And also we have taken care of the preemptive and non-preemptive failures. Apart from failures, a machine can have a maintenance. So when a resource is working on a particular entity and failure occurs, it will directly grow from a busy state to the breakdown state. So that particular change can be called as a preemptive failures. Whereas non-preemptive failures, a machine requires a maintenance monthly or weekly or monthly or in 3 months, something like that, periodically. So in that state, we don't want to stop the processing of that particular entity in the middle of it. We will finish processing that particular entity, then we'll change the state of the machine to break down and work on the system. So it's called non-preemptive failures. So advantages of this particular resource layer is that failures can be represented seamlessly both at the event level and the process level. And we have modeled two kinds of failures, that is preemptive and non-preemptive, and they can be contrasted easily. And for a new learner, it would be easy to grasp the concept of failures. And also we don't need any elaborate programming logic to implement this particular failures, and it's ideal for all levels of users to interact with. And integrated I/E² framework provides a set of basic process blocks for building process-driven models. Um, these blocks are built upon this existing framework, namely the resources, queues, and blocks. And however, the providing, I mean, the extensive usage of process-driven model and the usage of event-driven model entirely depends upon a simulation modeler's acumen to choose, make a right decision about choosing an event-driven model or process-driven model. And the common functionalities of the process blocks are included in the generic block class, and the subclasses of the block class can inherit them. And some of the blocks we have implemented are create blocks, seize block, delay, and release. And these all the subclasses of the blocks are dynamically binded by virtual keyword from the block class. So these are some of the classes I have developed, and I can just briefly go over the 2 or 3 blocks to explain the logic behind them. In the create block, when the create block is instantiated, the constructor instantiates entity and places that entity in the entity list. And there is a process entity method which will process the entity. And this create block, when when the entity goes through a process entity of the create block, another entity is created and it's placed in the entity list. So there is a continuous production of entities from the create block. And for the delay block, it's the simplest among the blocks. When the entities get processed at the delay block, it goes through certain delay at the block. So we simply increment the time by certain delay time, and we place it back to the into the event list, entity list. Sorry. And the events are represented by nodes and matrices as we discussed earlier, and it's simply a round block. And event arc is an arc without any entity, and this is the scheduling of future events. And this particular block, I'll discuss this in the coming slides. This particular entity, this particular arc represents the scheduling of future event with a tagged entity. Okay. This is an important topic in my research: enhanced modeling using entities in an I/E² framework. The importance of event parameters, event graphs, is event parameters. Event parameters is a parameterization of event vertices in a standard event graph. That means similar events can be represented by a single vertex, but can be differentiated by different parameter values. So all the similar events that are similar to event A are represented by a single node vertex called A, but different parameter values J. And this particular concept of event parameters allows standard event graph to represent a generic large systems in a very compact model. So all the submodels in a particular model can be represented by this in a very compact way by using the event parameters. So how are we using the concept of event parameters in our I/E² model? What we have done is we are representing the entities at the event layer, and event parameters is been replaced by entity, and all the parameter values are attached to the entity as its attributes. So this particular concept reduces abstraction of event parameters at the event layer, and it will give the intuitive feel of process-driven model at the event layer. And I will be discussing examples how the tagging of entity or representing of entities at the event layer will be helpful in building models. Okay, I will be discussing this model, and I will be showing an example by running my simple program. Here, what we have is integrated I/E² model. We have 4 blocks here: create block, delay block, event graph block, and dispose block. This whole thing is the event graph block, and in that workspace we are developing event oriented model. Process creates an entity, goes through certain delay, and enters the event graph block. Event graph block, when it enters event graph block, it has to enter through a enter event, and it has to leave the event graph block through exit event. When it enters enter event, it schedules an arrive event, and for that arrive event, an entity is tagged. The entity that entered the event graph, it is tagged, and that particular entity is stored in the queue. And the start process takes out it schedules the finish event. But when it is scheduling the finish event, it takes out the entity from the queue, updates the state of the resource, and tags it to the finish event. Once it's finished, the finish event when it occurs, updates the resource state variable, schedules another start event, and sends that event, sends the entity out of the event graph block by tagging it to the exit event. This might be very confusing for you, but I'll show you with an example. So we have a create block. I won't be going for delay block, and we have an event graph block here. Dispose block. Connect these blocks. Enter the data. So consider this as a create test. Let us consider the interval time is 5. That means every 5 minutes, entity will be arriving into the system, and the time of first arrival of entity would be at time 0. And for the dispose block, let's name it as dispose test. And enter the data for event graph. We have 3 events: arrive, start, and finish. Correct them. So an entity is entering the event graph through enter events. So we have arc with an entity attached to it, entity tagged to it. Again, start to finish, finish to exit. And we are scheduling another event from arrive to start. And when we done with the finish event, we are scheduling another start event. Now we want the resources and queues here. So add resource. How many resource units we want? We just want 1. That means 1 person is working in the system. And name the queue. Okay. And enter the data. This is the arrive event. And do we want any resource state change? No. We just want to increment the queue. That means we want to store the entity in the queue, increment queue, and enter data for the arc. What we want for the arc? We don't want any delay when we schedule a service, start service. But do we want to check any condition? Yes. We want to check if the resource is available. If we don't have any resource available, we have to wait in the queue. So we have to check if the resource is greater than 0. That means it is available or not. And this particular node or vertex is start event, and when we start the service, the resource is busy now. So we want to change the resource to busy state. That means we want to subtract the availability of the resource. So decrement the resource. What about the queue? Queue, we want to take the entity out of the queue and work on that one. So we want to decrement the queue also. And enter data for the arc. So when we start the service, we want to delay it for a certain time. So we want to delay the delay time would be 7. And do we want to check any condition to schedule a finish event? No. This one is a finish event. And once we finish with the entity, that means the resource goes from busy to the idle. So that means we want to increment the resource. That means we want to change the state. So resource plus plus. What about the queue? When we finish with a certain entity, we don't want to change any. We nothing to do with the queues. So there is no change. And for the enter data for the arcs, When we finish with that entity, we want to schedule an exit event. So do we want to have any delay over there? No, so 0. Any conditions to check if we are scheduling any exit event? No condition. But when we are finished, we want to schedule a start event. And when we are starting an event, we don't want to check any, don't want any delay. But do we want to check any condition? Yes. We want to check if there any entity are waiting in the queue, then we want to start the service. So we want to check the queue condition. This one and run the simulation. So for example, we want to check. Okay. Okay. This particular variables show the change of the variables. It will actually display the values of the variables. Right now, I'll run the simulation. It will confirm if I'm. So as you can see from the animation, first customer came. He sees that the resource is available. Then he seizes the resource. Then second customer arrives. He goes to the machine, and the machine starts working in. So while the first customer is working, second customer comes, and he will be staying in the queue like this. As you can see, two people are waiting, two customers are waiting, and the resource was idle, so it picks one entity from the queue and works on it. So the queue gets reduced. Right now the queue length is 2. Once the machine is finished with the one entity, it will pick up one entity from the queue. So we can actually represent the real life problems in this particular situation, and usage of event-driven models actually augments the capabilities of simulation modelers. And probably you might be worrying about the connection between these two blocks. That's a programming error. So end of the simulation. Similarly, we have worked on a problem called rework problem to demonstrate the explicit usage of entities at the event layer. So in order to truly realize the true potential of I-square framework, what we have done is we have taken up a complicated arena-based program, and this particular arena-based model, simulation model, and that particular simulation model evaluates the impact of retailer gaming, supply capacity allocation on supply chain costs. And this particular problem studies the activity between a supplier and 3 retailers under partial information sharing and different supply capacity allocation policies and retailer policies, and also the retailer backorder to inventory holding cost ratios. And simulation is applied to generate output in terms of input parameters, and some of the input parameters are retailer order up to levels, retailer mean demand, and retailer standard deviation, and supplier order up to level. And important entities in this simulation model are the clock entity. The clock entity, it will generate the retailer demand every day, and retailer demand also occurs at certain times, and retailer places an order once a week, and also supplier order occurs every day. So in this particular model, in this particular diagram, the blocks the blocks are represented by the supplier or retailer activity, and the arrows between them represents the flow of entities or flow of information. So retailer order entity is created every day, and he checks the entity, the retailer checks his inventory, and he comes up with his order. And if the retailer order quantity is equal to 0, then that particular entity does nothing and it is disposed. If the retailer order quantity is greater than 0, then that particular order is placed with the supplier. Supplier checks his inventory and sees if the inventory satisfies the retailer order. If its order is satisfied, then that particular order is satisfied. That particular order is satisfied by certain lead time, and order is delivered to the retailer. If the order if the supplier inventory does not satisfy the retailer order, then he fills the order partially, and he employs different supplier allocation policies. And the supply allocation policies and that particular logic is developed in VBA in Arena. So I mean it is a little bit complicated. That's why that it is the logic is developed in VBA and it plugged it to the Arena. As you can see the whole model here for the from the Arena, this particular portion of the model represents the retailer order activity, and we would be focusing on this one. And once the retailer order activities, I mean if the retailer order activity is greater than 0, and we have submodels here, VBA models, which work on the order allocation logic, and they are placed. I mean the retailer order is delivered to the retailers through this model, and this is a supplier activity submodels, and this is a system clock. And there are 3 retailers in the system, and these 3 retailers are represented by 3 subblocks. I mean here the retailer this particular submodel generates a retailer order, and this particular submodel retails the demand, inventory, and cost. And this is for the retailer 1, retailer 2, and retailer 3. So we I mean all the retailer variables have 3 sets of rows associated with their data. And for the retailer demand and cost activity, we have this particular submodel, and for the retailer order activity, this is the submodel, and we would be focusing on this one, and we would be explaining this one in detail in I-square model. So as I pointed out, this submodel represents this is the retailer demand and cost model in I-square model. As we had 3 retailers in the system, in the Arena model they had 3 submodels. But in the I-square model, we have like 3 create blocks, and these 3 create blocks creates the entities corresponding to each retailer, and they enter the event graph through enter event, and the logic in the simulation model represented by these events. And the I-square model, this particular event graph differentiates each entities by the entity attribute. We have entity attribute called entity dot retailer number. Depending upon that particular entity attribute, we are actually implementing the same logic to the 3 different submodels. So what are my contribution in this research? I effectively use the concept of event parameterization through entities. And what are the advantages of using the event parameters in the I-square model? We can represent the similar submodels and combining it to form a generic model. And the simulation framework we have developed efficiently handles entities just as in a process-driven model, and also it is very flexible, and it flexibly and explicitly handles entities at the event level. And because of the process-driven layer and the explicit representation of entities at the event layer, we actually providing an intuitive feel of process model even with the event level. And what are the advantages of that one? It enhances the appeal of event graphs to the modelers with a process-driven approach, a process-driven perspective. And also, it augments the simulation model's capability to handle complex logic without resorting to any programming language. And also, this intuitive feel of process-driven model and the handling of complex logic brings the simulation model closer to the real world, both in terms of simulation logic and also representation, model representation. And finally, this can be a good tool for the simulation, discrete event simulation learners to learn and understand the concepts of simulation, discrete event simulation. Any questions?
What can I do here that I can't do in Arena? Can I just do this in Arena? Or Lexim or one of the other commercial products that are out there? What can I do that I can't do in there?
What can you do with this one without what we cannot do it? I mean, the thing is like in Arena, whenever we encounter a complex problem, we have to go for a VBA programming, and we have to explicitly program over there. And for a simulation user without a programming background, it would be difficult for him to model the simulation logic over there. And this particular thing actually explains the entire logic in a simple event graphs and entities in entity terminology. And with those tools, he actually can represent the same kind of a complex program with a simpler tools.
Just as a follow-up, are you planning to look at a particular problem and then baseline it with your tools and then something like Arena, just so it's easier?
Yes, I mean, I discussed in this presentation, right? I looked at this problem. I mean, we have previously in our lab, we have worked on this particular problem, and we are planning to take this problem as a baseline and compare it with the model we have developed an I-square model, and compare these two models and see the advantages over the Arena model. By the way, why we have chosen Arena model? Because it's one of the popular and extensively used by the academicians and industrialistic industry people. Any other questions?